to leave my camera on. And mic off.
Did Matt? Cool. Well, thank you guys for venturing back over to Smith. Not as nice, but we will forge ahead and do some great mechanical engineering knowledge and wisdom gaining today. We're lucky enough today to have our own Lucas Meza. In case you haven't met Dr. Meza yet, which hopefully you all have, he got his PhD from Caltech, where he did a lot of work on ultralight metamaterials, and then he traveled across to the University of Cambridge for his postdoc, where he worked on 3D woven fiber composites. And, you know, it's been really fantastic to have him here at UW. I know it's never easy starting around or near the pandemic, which I realize is a lot of you in the room right now, but I've just been amazed at the collaborations he's been able to establish around campus and in many different domains that I'm sure he'll share with us today. But really looking at how we can use nanoscale architecture to build better materials across many different domains. And I know it's just the start to many great things. So with that, we'll turn it over to Lucas.
Yeah. All right. Thanks, Kat. Really excited to be talking to y'all about what we've been doing for the last 5 years. And yeah, building a nanomechanical experimental group in the middle of a pandemic was not fun. Today, there we go. Okay, so I'm going to be focusing the talk today on fracture toughness. Toughness is a really weird property. It's a difficult one to wrap your head around. I started this journey not actually understanding fracture at all, so I came from totally outside the normal fracture mechanics community and have tried to make some inroads in there, but from the bottom up. So to get started, the question that we ask with all of our research is, how do we make new materials that are better, stronger, tougher, lighter, et cetera? And you know, there's a science fiction version of reality. So funny, Kat, that you should mention Iron Man. This is like ideally what we want to do. I want to pull up this AI periodic table and just like moosh some chromium and some palladium and whatever together and make some magic material that's going to fly in an Iron Man suit. This is not how engineering works, unfortunately. Most of the time we have these Ashby plots or material property plots. So this is a plot of strength versus density. I have heavy, strong stuff up here at the top right, metals and ceramics, light and not so strong stuff down here at the bottom. And our goal is to push into the white space of these material property spaces, make things that are, as light as air, but still strong as a foam or a natural material, or taking some of the extreme strength materials like diamond that exists and actually turning it into something ultra lightweight that we can make use of in engineering. And there's been a lot of interesting case studies of that. My work takes two pieces of that puzzle, trying to break into these new property spaces, and that is architecture and nanomaterials. So I'm going to talk a little bit about what all of those are in the context of fracture mechanics. So architecture. Architecture is literally everywhere around us. There's a whole bunch of different architectural motifs that exist in the engineered and natural world. Most of you probably have a stochastic material sitting on your kitchen counter. Most of you are probably wearing a layered material right now. The layers in the soles of your shoe give you grippy things to walk on, but still squishy things so your feet don't hurt over time. Or you may have a reinforced sole for hiking, for example. Now that we're buying lots of stuff online, we see lots of corrugated materials, cardboard boxes. You're increasing the bending stiffness of a piece of paper by adding corrugation in there. And we're probably also wearing fiber composites. So all of our fabrics are not solid sheets of polymers generally. They're woven fabrics, either cotton or polyester or what have you, woven into a structure to be flexible and breathable. And so we've used architecture for a very long time historically. I am going to focus on this in the context of fracture. So dating all the way back to some of the earliest materials that existed in recorded history, we have straw reinforced mud bricks. If you take river clay, scoop it out of the river, set it on the ground, let it dry, it turns into a hard mud brick. You can fire it to make it stronger, but pre-fire, we didn't have the ability to do that. So we just let it dry in the sun. If you do that and let it dry in the sun without anything in it, it'll get really brittle. It'll start to crack. You can imagine the floor of a lake bed has those kind of cracked surfaces. And very early on, people realized if you just throw some straw in there, you can make something that is actually relatively tough. And so these straw reinforced mud bricks were used in engineering thousands of years ago. This is an ancient temple in Egypt that was used as a funerary ceremonial place, but this is a mud brick wall. So this is Like, engineers have been using architected materials for toughness for a very, very long time. There's a neat example of pre-colonial ceramics that use, this is pre-colonial Amazonian ceramics, again, taking river clay. In this case, the native tribes would take these glass sponges, break them up into small pieces, and weave the glass spicules into their pottery. And so they had special weaving or special pottery making techniques where they could get the spicules aligned with some of the radial directions and actually get things that were relatively tough. I was lucky to find a paper where they tried to replicate some of these, but some of these ancient pottery techniques, date back hundreds, if not thousands of years. So throughout human history, we've been using architecture to make tough materials. A lot of architected materials, a lot of engineered materials, we focus on strength and stiffness, but toughness, when is something gonna break, is really what you care about. My airplane can fly in the sky and the wings can bend and it needs to be strong and stiff. But if that wing explodes mid-flight, you're not gonna be a very happy camper. So toughness is the thing that governs that property. When is something going to break? So said toughness like 10 times now. What is toughness? So toughness, fracture, is the unstable propagation of a crack. We have flaws in material. These could exist as a large scratch on the surface or a notch milled into something, or an internal defect, a pore. When you apply a stress to a material, you get that you get that flaw to nucleate and unstably propagate in the solid. So this is fracture, unstable propagation of flaws. There's a couple different properties that we use to define fracture. One is fracture toughness. This is if I have a flaw of a certain size A, the stress required to propagate that flaw. So if I have a high fracture toughness material, I have to apply a lot of stress to get that flaw to grow. We also have energy release rate, which is confusingly sometimes called toughness. Also, so fracture toughness and toughness, not the same thing. They're related to each other. This is the energy that it takes to propagate a flaw. So one is the stress, one is the energy. I'm gonna pull up another Ashby plot here. This is now a plot of fracture toughness versus Young's modulus. There's a lot of stuff going on here, so I'm gonna actually hide most of that. So fracture toughness and toughness relate to each other based on the Young's modulus. So I can actually draw an iso line of G toughness here. So here, this diagonal line is my toughness. And this is actually when we think about materials that are tough and resilient, intuitively, we actually think about G toughness. We don't think about fracture toughness. As an example, here is soda lime glass in that plot. So this is our standard window glass and natural rubber. So rubber, very soft, very compliant, but also very tough, difficult to tear rubber apart. Soda lime glass actually has a higher fracture toughness than rubber because it's stiff. It takes a lot of stress applied to it to get it to break, but it has orders of magnitude less energy in the fracture process. So that G is way, way, way lower for rubber. There's one material in particular that I want to point out here, and that's leather. So leather, this is treated leather. Leather is skin. It's our natural barrier to the world. Is actually one of the toughest natural materials that exist on an energy basis. So you see here, it's kind of at the top edge of some of these material property spaces in line with some of our nickel titanium superalloys that we use for jet engine turbines. And when we look at what happens when we try to break leather, this is an in situ fracture test on a piece of leather. You don't have a crack that just propagates. You have extensive damage. Pretty much all natural materials do this. Leather is remarkable in its ability to do this. So I love showing this video. It's super cool just watching all these fibers pull out. But you don't just have a single flaw nucleate, you have a wide dissipation of damage events. So this distribution of damage is what gives leather its toughness. And pretty much every natural material does this. This is an example of shell doing this. And bone, not only does nature do this, but it does it all the way down to the nanoscale. So this is an interesting paper with one of my collaborators, Otmar Tuliano, now at Penn, where he took a microscale section of a trabecular bone, put it in an SEM and did a microscale 3-point bend fracture test on it, and showed that you actually get collagen nanofiber pullout in the bone. So all the way down to the nanoscale, natural materials are toughening. And you can see increases in energy release rate all the way down to this nanoscale, nanomicroscale. So natural materials not only have these interesting fracture toughening mechanisms, they have them at every length scale, all the way down to the nanoscale. And the end result of this, and what makes fracture very unique, is there's no rules governing fracture toughness. For strength, stiffness, if I take two materials and I moosh them together, it's pretty much the average of those two that is going to be my property that I end up with. I take the volume weighted average of the two. I can't exceed a rule of mixtures for stiffness. I can't exceed a rule of mixtures for strength. Toughness, if you look at, this is a conch mother of pearl. The stuff that makes up conch shells is nacre and aragonite. Aragonite, it's like a, it's bioceramic. Nacre is 90% of this, 90% of it is this bioceramic. If you took a rule of mixtures between those two materials that make up nacre, you would have a very, very low toughness. But what you see is something that is orders of magnitude higher. So nature is making use of something in these toughening mechanisms, some sort of toughening mechanisms across length scales to derive this enhanced toughness. And this is really what drew us in. Natural materials show all of these interesting architectures and demonstrate that there's just no limit to where you can go with toughness. So this is really what sparked our interest. And I think the interest of a lot of other folks as well. So over the past 20 or so years, we've seen lots of examples of engineered materials that try to mimic the structure of natural materials. This is a brick and mortar structure that's meant to mimic nacre out of Berkeley. This is a Bouligand metamaterial meant to mimic mantis shrimp claws, dactyl claws. So you have twisted fiber structures. This is out of Purdue. Interpenetrating lattices meant to mimic some of the lightweight lattice structures that you see in nature, like weaver bird nests, for example, that are difficult to pull apart, and bio-inspired glass. So when you incorporate just any of these architected material strategies, you start seeing toughening mechanisms emerge. The big thing when we were getting into this that I think all of these folks missed was the length scale. Maybe not missed, conveniently ignored, because it's very difficult to do teeny tiny tests. So we see natural materials are engineered at the micro and nanoscale. It's hard to do that with engineered materials. So this was our charge. This was our goal, is let's see if we can understand toughness at fundamental material length scales in a way that lets us understand the natural world around us and how to really push to the boundaries of engineered toughness in materials. So I'm going to talk about a few different projects here. We started off with nano-Bouligand structures. That'll be the first story that I tell. That led us into thinking about what ductility was to begin with. We started off with complicated architectures and then we went very simple, then started building it back up into slightly more complicated architectures with layered structures, nanofoams, spinodal architectures, and interpenetrating lattices. So we'll see how much we get through. My goal is to talk through all of these. We'll see how much we talk about. All right, so we're going to start with nano-Bouligand structures. This is work that I started in 2019, and then 2020, we were using the WNF and the MAF and slowed down a lot, tried to keep it going, and eventually got some stuff out in 2023. This was a lot of the work done by my first PhD student, Zainab Patel, who just graduated last year. So you'll see her a lot in here. All right, so this is a nano-Bouligand beam. These are, you can look at the scale bar here. I was going to bring samples, but my samples look like specks of dust on a chip. And so I could have passed that around, but it's not actually much to look at. You can't see it with your bare eye. This is an 80 micron length beam. For reference, the thickness of a standard piece of computer paper is 100 microns. So the length of it is thinner than a piece of paper, or a human hair is about 50 to 100 microns in diameter. So this is smaller than all of those things. This, again, looks like dust. The smallest feature, we write these using two-photon lithography. I'll talk about that in a sec. The smallest features on here are these nano line traces. These get down to about 500 nanometers. And we build these into different architectures, different twist angles. We actually fully print this whole setup. You'll see some debris. I'll talk about what that comes from in a sec. But we're designing this to do a fracture test. Fracture is a difficult test to do. We had to print our own setups in understanding this. Oh, I did add the TPL thing. I didn't delete that. That's fine. So we design these numerically. We have Python codes to do voxel level control over these prints. So we manually define where all of these lines go. This is done in a two-photon lithography process. So like stereolithography, SLA printing, if anyone's familiar with that, we use light to expose to cross-link material. We can just do this with an infrared laser, so it gets cross-linked in a very teeny tiny spot size. Minimum features about 100 nanometers, 150 nanometers, and you take that and you trace it around in space to create these architectures. So this is where we started with, this Bouligand beam, actually with a lattice substructure underneath. And my slides are auto advancing, and we'll see. Okay. We actually have to plasma etch to remove the substructure underneath this. So we want a freestanding beam, but if we printed it freestanding, it wouldn't survive. It would just fly away when we developed it. So we etch away this lattice with a plasma, and then we do fracture testing. And we tested out a range of densities and a range of twist angles here, trying to sort of explore this parameter space. This is what one of the tests looks like. This is in situ fracture testing. So this is done inside an SEM. This is a nanoindentor that lives on a little platform that we plug into an SEM, and we do these tests. When we're analyzing these, we get load displacement data out. So much like you would with a standard Instron test, we actually superimpose a sinusoid on top of that, so we can measure loading stiffness kind of continuously during the process. From that unload stiffness in the test, we can figure out how much the crack has grown in the material, and we can use that crack growth along with not linear elastic fracture mechanics, but elastic plastic fracture mechanics. So there's some ASTM standards that define some of this to get J. So this J here is related to G, energy release rate during fracture. The J is the evolution of that. So eventually when you have a fully developed, it is G, but J, G, just keep them kind of the same in your head. In terms of defining material properties here, we, in this particular study, looked at this one layer crack growth. So you can see it's difficult to track exactly how this crack is evolving over time, but we looked at the J, the energy released after a crack had grown one layer in all these materials. So you'll see a lot of J1Ls being reported here. Sort of an arbitrary metric, but useful for the architectures that we were looking at. Okay, so this is what all of that looks like together. This is now a fracture test on a 0 degree material. So all of the fibers are aligned in the beam direction. We can see the crack grows, we get a rising J curve, and the crack propagates, relatively quickly through the solid. When we have a twisted material, you'll notice that the crack propagates a little bit more slowly. It's a little bit more difficult to get that going through. We have a higher J resistance to that crack growth. When you look at these kind of side by side, a solid beam will have a crack that goes through relatively rapidly. As you reduce the density, you actually notice the crack doesn't propagate as easily in the solid. So this was an odd finding that I'll talk about more in a sec. And when you have higher twist angles, kind of the same thing happens. That twisting of the layer really impedes crack growth. And so this alone was an interesting result, but we wanted to figure out what really was going on here. If we look at load displacement data for these different architectures, for high, medium, and low density, this is 50% dense material, you have kind of, as you would expect, a decrease in the strength and stiffness. If you reduce the amount of material, you're limited, you're Voigt limited, you can't exceed a rule of mixtures. My strength and stiffness is going to decrease proportionally to the amount of material that I'm removing. And if I twist my fibers out of the direction of loading, if I am applying a bend test on a 0 degree versus a 90 degree, it's going to be a lot less stiff when I'm applying a load orthogonal to the fibers. But the J was not that. And so when we look at the energy dissipated, that J1L, for all of these different architectures, there's actually not a drop off at all. So the toughness here was not following this rule of mixtures. And when we look at some of that data and we zoom in, I'm just going to focus on the 0 degree twist angle. So this is all the fibers aligned with the twist, aligned with the beam. We show that when you reduce that density from something that's about 80% dense to 45, 50% dense, you actually maintain your toughness, which is weird. Because if you just look at a rule of mixtures, if I take out half my material, there should be half as much stuff dissipating energy. Where is all that energy coming from? So this is not what we're seeing. I'm not seeing any sort of a rule of mixtures. And what is actually happening here is in reducing that density, you're starting to create nanoporous structures, nanoscaled voids. Actually, as a printing defect, the fibers are a little bit wavy. So even though it's like 50% dense, we don't have beams that are just going to fall apart. There's kind of like periodic interconnections between them. So you end up with almost isolated nanofibers. And when you look at the toughness of nanofibers alone, it turns out nanofibers are more ductile than their bulk counterparts. If you make a polymer nanofiber, it ends up being stretchier than a bulk material would be. We showed that experimentally using some of these different loads. The lowest density material had a much higher strain to failure. It was stretching more before it started to break. And so what we're seeing here is actually size-enhanced ductility. So we're getting more plastic energy dissipation, we're getting more ductility in the material by creating these nanoscale voids, which was an interesting first result. But why? Why is it more ductile? So that's where we got stuck on next. So we started to rethink ductility. This is not something I was expecting to do. I thought we understood ductility, plasticity. We started this kind of just as a one-off, trying to get some material properties, and ended up turning into a really interesting story. This is where some of my other PhD students now, Kush and Aziz, start to come in, working with us on this. So instead of creating an architected fracture sample, we just wanted to make solid beams. So got rid of all the twisting, all the layering, made these solid single edge notch beams. In the printing process, we can control laser power. By controlling laser power, you can change the degree of cross-linking of the material. You can also use heat treatment to additionally cross-link your material. So if you expose it to a little bit of laser light, you have polymer chains that are a little bit bonded together. If you heat it up to about 200 C, they get really, really stuck together, so increasing the degree of cross-linking. You can quantify that degree of cross-linking using Raman spectroscopy and correlate the writing parameters, in this case laser power or temperature exposure, to an end degree of conversion. So here the lowest degree of conversion, where it actually stays together and doesn't just dissolve, is about 17%, and the highest we got was about 80%. So those are our two bounds, 17 to 80. So when testing these, we were starting to do fracture tests. You'll see, this one flies away. The very low degree of cross-linking one is very, very ductile. It's nice gradual deformation. You see it's the blue curve here, pretty much a nice stable load plateau, ductile tearing. The 27%, you see a load drop, a stable-ish fracture. When we tested this DC80, 80% one, Zainab thought we did the test wrong because she said the sample disappeared. I was like, no, it's just so brittle that it flew off the chip. Don't tell the SEM technicians. They will not be very happy. So we made teeny tiny polymer samples all over the SEM somewhere. But you see this kind of catastrophic load drop. So this is indicative of a very, very brittle fracture. And so looking at the J, these all initiate at a similar J, but this lowest, the lowest degree of cross-linking one has a much higher energy dissipation. You can see the sort of inverse correlation. As you increase degree of cross-linking, you increase your stiffness and strength, which is normally desirable, but you also drastically decrease your toughness. So you're getting 4 times increase in stiffness, but 6 times decrease in your energy dissipation toughness. So this was the data we were looking for, but that doesn't explain why it was more ductile. So to do that, we actually had to go down a rabbit hole, down a really deep rabbit hole. And this is where Marco Salviato, our collaborator, has helped a lot in our understanding of this. In a fracture process, you saw there's this little ball of energy that propagates in the solid. So you have a flaw, you create a stress, that ball of energy grows to a finite size. That is the J or the G, that's the critical strain energy release, and then that propagates unstably through the solid. Now, in that zone, there's actually 2 regions. So outside, there's an elastic zone, there's some plastic energy dissipation really close to the crack, and then there's damage. So a plastic zone and a fracture process zone. The size of this, we call an RP. The relative ratio between these is important for a range of things that I'm not going to talk about yet. But when you plot out now the size of the sample relative to this fracture process zone, where D naught is a non-dimensional figure of merit that's related to the, D is a length figure of merit related to the RP with some geometric corrections in there. A material that's very big relative to that RP, you can do linear elastic fracture on. This is what all of our ASTM standards are designed for. You have big sample, small RP, I can bend it and I get a KIC out of that. But when my sample is small, I end up falling into a strength governed regime. I reach kind of a theoretical plateau strength of a material. So these are theories that have been around. Zdenek Bajant at Northwestern is a pioneer of this, has been doing this since the 80s, mostly for concrete, mostly for brittle materials, and never in the context of ductility. They just kind of say, oh, it broke or yielded, and then that's it. So what we did, we took the way you actually get some of these data points on here is you make beams of different size and you test them. It's literally it. You make big, small, smaller, and you break them and you see what strength they break at. And that's how you plot out the space. And then you can get some material properties. We wanted to then see if we could understand our ductile to brittle transition in the context of this fracture size effect, the size affected length of fracture. So we did numerical modeling because it's actually difficult to do a fracture test on with nanoscribe samples, something that's 3 millimeters or 1 micron. We're somewhat limited in how big or small our samples can be. When we look at this numerically, you can see the lowest degree of cross-linking and the highest degree of cross-linking samples. This DC80, you get this kind of nice characteristic damage and plastic zone that gets fully developed and then unstably propagates. In this DC17, you actually not only don't see a hardening, you don't even see damage developing. When you look at the size of these zones now, that RP, LC, focus on the RP right now, this whole sample is 26 microns thick. That was our beam dimension size. Here, the RP for the highest degree of cross-linking was 5 microns. So 5, 26, we're much smaller than the size of the beam. We can fully develop our process zone. It fully develops, unstably propagates in the material. The DC17, that plastic zone size is 280 microns, so 10 times bigger than our sample size. Not only that, the damage zone, the LC, the fracture process zone, is 115 microns, also way bigger, 5 times bigger than our sample. The sample is too small to actually develop damage. So what we see is ductile tearing. This is a fracture size effect. So if I take that same material now numerically, that 26 micron beam with that 280 micron radius of plasticity, I see ductility, this nice gradual tearing. If I took that same thing and I made it 3 millimeters, much, much bigger than the size of the sample, I get a brittle behavior. Same material, same degree of cross-linking in this case, now size affected. If I took that DC80 material, that 5 micron, I had a fully developed plastic zone. If I turned it into a 1 micron beam, I would see ductility. We can do this numerically a lot easier than we can experimentally, so these are all numerical. So ductility in and of itself is actually a fracture size effect. There's no such thing as a ductile or brittle material. There's only materials that are ductile or brittle at the size at which they exist. So this was our rethinking ductility. There's been a whole bunch of results through history on brittle to ductile transitions, dating back to the Liberty ships. I show this in one of my intro mechanics of materials classes. We made some ships, put them in a harbor in Oregon, they cracked in half, and we're like, oh, why? Why did that happen? I need to understand fracture mechanics better. And so there's been a lot of work in looking at temperature affected ductile to brittle transitions, microstructure affected, size affected. All of them look at, I take a sample and I break it and I have some energy dissipated based on these temperature affected changes. What they've actually been seeing, and we're trying to write a review paper summarizing this now, is they've induced a ductile to brittle transition based on this fracture size effect. So they have, for these very cold materials, the size of the zone shrank, fair, and they got a brittle failure. But the ductility that they're seeing, the energy dissipation, actually came because this is done with a standard ASTM Charpy sample that's, 5 millimeters across and 8:1 aspect ratio beam with a notch in it that's at a 45-degree angle. There's your Charpy impact standard. They accidentally stuck themselves into a hole with these standards that locked into materials that are ductile or brittle based on the size that they are. If you made this thing half the size, you wouldn't see this transition here, you would see it a little bit lower. And material scientists have been seeing this for a very long time, for decades. This is an example of an alumina sample, so alumina brittle ceramic, in situ TEM tension. You can see some ductility there and actually a necking prior to failure. So when you make materials small, you actually start to see ductility. This is an example of a silicon nanopillar. You see size-affected ductile to brittle transitions. This is from 2019. Metallic glasses, also very brittle materials, ductile to brittle transitions. Gallium nitride, nanopillar, ductile to brittle transitions. These are things that material scientists have seen, again, for 10, 20, 30 years in some cases. We've known that this is a thing, but nobody has actually looked at it in the context of these fracture size effects. So we're trying to now go back to all of these. We're writing a review paper now. Stay tuned. Hopefully in the next year or so, we'll be able to publish actually what we're seeing in engineering. All of these ductile to brittle transitions, temperature affected, size affected, architecture affected, are fracture size effects. Okay. How are we doing on time? 1:30. All right. Cool. Making good time. So how do we build this into architectures now? We're going to do something very simple. The simplest architecture that I can think of, which is stacks of paper, layered materials. I can go here, I was making solid beams for rethinking ductility. Now we're going to take that and we're going to split it up. So 1 degree of architecture. This is also a continuation of that same work, Zainab Khosh-Aziz. Here, there was something that I kind of gloss over with the 2-photon process. When you cross-link a material with a 2-photon process, you actually get a gradient of cross-linking. So at the center of the line, you have a higher degree of cross-linking than you do at the edges. What that means is you can actually, by tuning the spacing between the layers as you write them, I can write layers, say this is 1.6 microns, I can make a layer spacing that is 1 micron, all of these overlap, and I get something that is relatively homogeneous. I can also take it, make it almost the size of the voxel, and I get the heterogeneity that is there in the line write, and then I can write it further apart and actually make something that's totally separated. So we use this kind of natural feature of the 2-photon process, created things that were solid, heterogeneous, and then separated, and use this as a tool to test out architected heterogeneity and size effects. So there we go. These were all written just with the tool itself. We didn't do any heat treating, so the max degree of conversion was 45%. So somewhere not super, super brittle like the heat treated ones were, but not very ductile. Okay, so this is the solid beam. This is now similar fracture test to what you just saw before. Relatively brittle, relatively fast load drop, not catastrophic. It didn't fly off the chip, so you still see cracks growing. Note that the playback speed is 160 times. So this is actually a very long slow test. It takes like 10 minutes to do, but sped up here. When you start increasing heterogeneity, you start seeing a rising J curve. You see a much more stable crack growth. Now you have the zipper mechanism as the crack propagates through. When you make these just spaced out, so just not touching each other, you now see a very stable crack growth. You can see it zips through one layer and then gets stuck, zips through another layer, gets stuck. And then if you make it too far apart, you actually won't see it propagating through at all. It'll start to split off. And so you start seeing some crack redirection. So we can't really call this a fracture property. These are really nice to see all stuck together. The 1 micron sample, relatively brittle. The more heterogeneous sample is more ductile. The fully separated samples now are very, very ductile and very difficult to break. So what we've done here, we did some numerical modeling on these to try to understand all of these processes. So here you can see the dense sample, crack propagates through, heterogeneous and separated materials. You see a more gradual crack propagation through. This is important for understanding the size and extent of the plastic zone. What we've started to do here, though, is actually induced ductility in our material. So we have, for that DC45, the radius of plasticity is around 8 microns. All of those individual layers we saw were about 1.5, 2 microns total in height. So all of these layers, actually, when they're fully separated, are ductile. We've created a ductile material by virtue of a fracture size effect. You also have an effective architecture. So when a crack propagates from a stiff to a soft material, it's easy to go into the soft material, but then the stress drops and it has to reinitiate that crack into the stiff material. So that phenomenon has been known for a while. This is architected heterogeneity. So if you just take E1, E2, different materials, different stiffnesses, you get this sort of toughening effect. What we're seeing, though, is not only this architected toughening effect, but a size-enhanced ductility toughening effect. So we're getting, by removing material, this is an actual absolute energy dissipation. We're making something that is 6 times more energy dissipation. It has 6 times more energy dissipation by removing material, by making it spaced out, all by inducing this fracture size effect. So what we've done now, we have to think about this in the context of, you have a material radius of plasticity that we talked about a second ago. Now you have a new emergent architectural radius of plasticity. And what is happening in these solids as you start to introduce separation is you enlarge the size of that plastic zone. So I have that plastic and damage zone. When I start creating these layered architectures and I force a crack to get stuck and redirect, that plastic energy dissipation has to happen somewhere, and it ends up getting spread through the sample. So what we're seeing now is not just, a nice, maybe like kidney bean shaped radius of plasticity. I have to understand the length and depth, or the extent of that plastic dissipation that's happening in the material. So I'm getting now a material and an architected size effect. And this is what is happening in nature. If we look back at natural materials, nacre, if we look back at Euplectella sponges, these are sea sponges. These are made of mostly ceramics. And the layer spacing, the size of the layers that you see here is on the order of tens or hundreds of nanometers. Nacre platelets, you see there's a 2-micron scale bar. This is 500 nanometers thick. And it's 500 nanometers thick for a reason. And that reason is that it's just small enough to start being plastic, where you're starting to activate this size-enhanced ductility in the individual layers along with an architected ductility. So you see natural materials are great at not breaking. They're doing this so that you can see this kind of quasi-ductile or quasi-brittle behavior, kind of gradual bending of, take these sea spicules that are like 99% ceramic silica for the Euplectella sponge or calcium aragonite for nacre, and you see ductility. And there's been a lot of discussion on, toughening mechanisms, how the zigzag or the soft layer in between these things is affecting the properties. I think we still need to prove this, that this is all a fracture size effect. So we're in the process of getting some of this out. Hopefully we'll start to change some of the conversation around how we think about material ductility. Okay, let's talk about nanofoams. So nanofoams, this was one of the early big collaborations that we had. Vipin Kumar, Marco Salviato, the other PIs on the project, Kush and Santosh, yep, they're both here, were big players in this. This started off, so foam mechanics has been around for a long time. We've been making foams for a very long time. We've understood their mechanics reasonably well, what we thought for a long time. The strength and stiffness of foams generally scales with density. So if I reduce the density of a foam, I am limited by the Voigt bound, which is a linear scaling. So if I take half of the material out, I get half the strength and stiffness. Most of the time for foams, which are stochastic, I get a little bit worse than that. So if I take out half, I get maybe a quarter of the stiffness or a quarter of the strength. Depends exactly on the foam architecture. Fracture toughness for foams was, I thought, a reasonably well-developed thing. For foams, or for fracture, you have to have a length scale. There's a size of a flaw, and for foams, there's a size of a unit cell. So actually, foam fracture toughness didn't just depend on relative density, it also depended on length scale, so the size of the foam. So these kind of classic foam fracture scaling laws said, if I take a foam and I make the pore smaller, I will end up with a less tough material, and it'll scale approximately with the square root of the cell size. So, 1/10 the cell size, 1/100th the cell size, 1/10 the toughness. Yeah, so Vipin, it turns out, had some very interesting results in his lab sitting around that counteracted this idea. So Vipin works on solid state foaming. I'll talk about that in a sec. He had been doing these impact tests on micro and nanofoams, showing that microfoams under impact at the same density were relatively brittle, but nanofoams were not. Nanofoams had this enhanced plasticity, this pullout. These were drop tower tests in the ME testing lab. And in some cases, by inducing that nanoporosity, you actually had higher energy dissipation than just the base material. It got tougher than the base material, the base polymer itself. So these were done on PEI, polyether imide, high temperature, high performance thermoplastic. Around the same time I started, there was some results coming out of my former group in Cambridge, so I knew about it, where they were looking at doing fracture tests on micro and nanofoams, showing that nanofoams were much, much tougher. So we saw this is a KIC. They weren't looking at J, which wasn't quite the right way to do it. We saw these results and said, okay, something is happening here. What is going on with these nanofoams? Why are these tougher? Why are they behaving in a different way? So coming back, we started trying to explore this nanofoam parameter space, nano and microfoam parameter space. These materials are made with solid state foaming. This is a technique that Vipin is a pioneer of and has been doing for quite a while now. In this technique, you take a thermoplastic polymer, put it in a high pressure chamber, saturates with CO2. Generally, any inert gas sort of works. CO2 works better than most. you have a certain amount of CO2 that dissolves in that material. You take it out, heat it up, and the dissolved CO2 nucleates as bubbles. The amount of CO2 that you've nucleated into the material determines the size of the bubble. So if you put a lot of gas in, you end up with smaller bubbles. There's just more bubbles nucleate. You get nano or micropores. So if you put a little bit of gas in this case, 1 MPa CO2 saturation, you end up with pores that are on the order of 5 to 30 microns, depending on exactly the parameter condition. You can control the temperature of the foaming process and control relative density. So you have a nice control of 80% to 50% dense foams. And you can do that at a higher pressure, get nanofoams, so now nano-sized bubbles around 10 to 40 nanometers in diameter with similar densities. So you can explore that 70% dense to 40% dense parameter space. And we wanted to see if there was a demonstrable difference in the energy dissipation between these materials. So we could figure out why were we seeing these odd results with nanofoams and not with microfoams, and not even necessarily with the base material. Like they were outperforming the base material in some cases. So this is some of the excellent work of Kush and Santosh. These are DIC experiments, so digital image correlation tests on uniaxial tension samples. You can see this is the neat PEI on the left side, and then the lowest density foam on the right. These actually form what's called a Luder band. So you have a softening region in the PEI that propagates through the solid. Interesting phenomena. But you see, this is actually, from these tests, you can get a true stress strain behavior. These are very difficult to get experimentally. Most of the time we report engineering stress strain because it's hard to do these. But yeah, these we were able to get true stress strain. And we did that for micro and nanofoams. So here's micro and nanofoams. The end strength and stiffness of these was relatively comparable. We saw similar behaviors. If you look at property scaling, these fall where you would expect foams to fall. You have that range of properties for Young's modulus and strength. They fall somewhere in there. There was a point where these had a lower strain to failure, which was actually an interesting point that I'll talk about in a sec if I don't run out of time. We also did fracture testing on these materials. So these are micro and nano fracture tests. So this single edge notch double clamped specimen, also DIC. You can see the full plastic energy field as this dissipates. So the lowest density foams are relatively brittle. You have a small zone that develops and then a crack grows through. The higher density foams, you can see extensive plasticity. So a lot of plasticity in the material. And interestingly here, PEI is this curve in black. Microfoams, when you start reducing density, you see a lower toughness. For nanofoams, we actually saw a higher strain to failure and more area under the curve for these nanofoams. Something was happening differently where this was actually exceeding the performance of the base material. When we look at the energy dissipation for these foams, this is just a linear scaling. There's not great rules for density, foam energy dissipation with density. You can actually see that highest density nanofoam not only exceeds the rule of mixtures, but exceeds the absolute energy dissipation of the base PEI material. If you look at that law that we talked about before, this kind of predicted scaling law, if you try to plot KIC normalized by length scale, it's entirely off. It doesn't correlate with the size of the pore at all. And if you try to look at it, with density, it doesn't correlate, and with length scale, it doesn't correlate at all. So all of these, this kind of classic rule of mixtures that we saw with foams doesn't apply for these micro and nanofoams. So why was that happening? To understand that, we had to go to numerical modeling to piece apart how much energy was being dissipated in fracture and in plastic energy dissipation processes. This is some of the excellent work by Kush. We have a crack band plasticity model where we're able to match the true stress strain behavior of the material. And we can actually pull out not just the work of fracture of the material, but the individual contributions of work of fracture. So we can see that between micro and nanofoams, you're not actually getting a lot of, here GF is the damage, the fracture energy dissipation, GP is the plastic energy dissipation. So what you're seeing now in going from a micro to a nanofoam, you're getting a little bit higher fracture energy dissipation, but you're getting double the plastic energy dissipation. So something is happening in these nanofoams by creating these exposed nanopores. We're still working on this, doing some molecular dynamics modeling to piece of art exactly the mechanisms, but we see size enhanced ductility of that nanofoam. So something about the nanoporosity is actually enabling the motion of the polymer chains that's giving us much, much higher plastic energy dissipation, in some cases, again, exceeding that of the base material. So yeah, this was a really interesting piece of work, still ongoing, still getting some stuff out. I'm gonna run out of time to talk about gradient spinodal structures and interpenetrating lattices. So I'm gonna jump through these really quick and just show these are thin shell ceramic metamaterials that we engineered with a whole bunch of different architectures. When you make these thin shell hollow ceramics, generally these are recoverable. So you can see this is an isotropic structure, gets compressed and then bounces back fully. This is some of the work that I related to work that I'd done in my PhD. This is the shell buckling induced phenomena, and buckling is elastic. So you can make something that is a ceramic, but that is bouncy for a whole bunch of different architectures. But when you make it thicker, you start seeing damage. So ceramics break. If it gets too thick, you'll see fracture instead of buckling, and you won't see any recoverability in the structure. But when you start to introduce gradients in the structure, we still see fracture, cracking, but these structures are actually able to fully recover. So what we've done, I think, and I'm gonna skip through lots of stuff here, did lots of numerical modeling, trying to understand fracture, stress concentration sites. What we've done now is in a quasi-brittle material. This is a material with very limited plasticity inherently. We have in the isotropic structure a very small damage zone size. So this zone fully develops, you get a crack, it cracks, the material is broken. In our gradient layered materials, the fracture process zone is actually bigger in this case than the size of the layer itself. So even though the material is brittle, you can start to see damage, but if you don't develop that fracture process zone fully, you don't get catastrophic failure. So you get something that is able to recover despite cracking, despite experiencing a lot of local micro damage, and fully recover after compression made from a ceramic. Interpenetrating lattices is really fascinating too. This one is also a set of really cool experiments. A lot of these are done by Zainab and my student Aziz. I'm gonna skip through them, but the end result is kind of similar to the layered structure where we can induce ductility in the individual fibers and the individual beams in the structure and get an architected ductility effect on top of that. So yeah, that's where I'm gonna stop because I know I'm out of time. A whole lot of stuff. Hopefully I've helped you understand fracture better, if nothing else. Fractures are a tough subject. I know, I have to do it. But we're really plunging the depths of fracture and really revealing how little we know about a lot of these things. So there's a lot more to learn with that. Thanks. I didn't even get to talk about some of the cool work we're doing with other collaborators, like Al Nelson on campus with some of our biopolymers and Brad Boyce for the interpenetrating stuff. But yeah, thanks, and I'm happy to take questions.
Molecular dynamics, what are the simulation of your numerical?
So most of what I do is finite element modeling, and we have some advanced material models to get tension, compression, asymmetry, damage, but that's the extent of it. I know finite element modeling pretty well, and we have collaborators who we work with to do molecular dynamics. So Marco Salviato can do some. We have Monica Alvaro de la Cruz for some of the biopolymer stuff that we're doing. Yeah, but that one, I'm an experimentalist. Even doing finite element was like, I did it during my postdoc and I learned to do it there for a reason. But that's sort of the extent of my numerical toolkit is FEA. Yeah, I mean, this is where like eventually we're trying to get to what nature is doing. So like the structures that you see, if you're trying, it depends on the type of architecture you're using. Like the reason mother of pearl opalesces is because of those layers. It created a photonic crystal on accident, so it looks cool. But like bone, shell, these are all, they don't look necessarily remarkable. Wood, wood is a really tough architected material. it doesn't look necessarily different than a normal material would, but there's a lot of engineered architecture within the material itself. So yeah, this is something as engineers, it's really hard to do. We've sort of played metallurgy magic tricks over the years. That's the extent of how we design materials. It's like, let me increase the chromium content by 0.1%. Oh, I made a super alloy. But look, these nano precipitates, but it's not intentional. And that's sort of what you have to do. Like, I can't nano 3D print a table. I can't nano 3D print anything, like anything sizable, a puck. But yeah, this is really trying to inform how and why we should be designing materials in the way that we do. Like, why does it matter that this is a 500 nanometer platelet versus a 10 micron platelet? Who cares? Like, why is that tougher? This is why.
Is there any other type of lithography that's looked at, or is it because it's so small, lithography really don't?
So there are a lot. Let me see. I'm an expert in two-photon lithography. I have. Here we go. So I had an intro slide that I skipped over because that wasn't the focus. A lot of this started 15, 20 years ago with self-propagating photopolymer waveguides. So lithography, but directed lithography with then thin film coatings on top. So this was out of HRL Labs. They made the world's lightest material for like 3 months, and then they got beat by somebody else. But it's a really cool picture. It's like a metal lattice sitting on a dandelion. You can use stereolithography just with microscope objectives to scale down the feature sizes. You're limited a little bit by the wavelength of light. You just can't beat physics at some point to make things teeny tiny. Self-assembly is really the way to go. This is like what we want to do, is throw things in a vat and just have the microstructure pop out. But there's a lot of design that goes into self-assembly, like chemical design, that is way, way outside my wheelhouse. And I'm very glad I have chemistry collaborators to do the chemistry for me. Yeah, so this is like a very hands-on way of designing a structure. It's just a nice tool. Yeah, but that self-assembly is the ideal, just not yet. Yeah.
Sadly, there is a class in this room afterwards, so we have to call it quiz with questions, but welcome to talk with Lucas more in the hallway afterwards, but join me in thanking Lucas.
Thanks.